this is the second, let's say, talk. The first talk has been given at the campus south, and this is the part for the design of materials. It's a pleasure that we are, let's say, hosting you. And please.
The pleasure is also mine. So thank you, Stefan, again for the nice introduction. And it's really an honor for me to be part of you. And the KIP Fellowship is great. And I thank the KIP Fellowship for supporting my stay here so that I get to do great science with the great colleagues here. We begin again.
Yes.
We don't just go from here, right?
Yes.
So what was I talking about? Trees, yeah? So this is a model of a tree. You can see that the branching pattern here is repeated over several levels of structure, going from the main branch to the smaller ones. I hope you can see. And in this real tree here, this self-similar pattern, it's called self-similarity. Self-similar pattern is making for a complex structure, right? You see, the closer you look, the more branches you see. So exactly how many branches do we have? No, there's some sense of uncertainty. Life is complicated. And also they call it fractal. Oh, we don't need to get rid of that, right? Yeah, okay, so good. It's not my problem. Yeah, where was I? This fractal is also called self-similarity, and it's also shown in here. This is broccoli. It's called the Romanesco broccoli because each cluster has smaller clusters, like and so on. And fractal, as you may know, is very common in nature. This looks like some mountains, but it could just well be some river system. Okay, you see this? This is a big molecule that's closely mimicking this tree model here. This molecule, you can see it's a radiant shape. It's a starburst. Okay, but it's really like the tree, and it's very big. You see the molecular formula. It's like the protein. You see over 1,000 carbon atoms. And as chemists, we can put on different functions. Here we are putting like amine groups on this gigantic dendrimer molecule. It's on the surface, and these amine molecules, they can take on positive charges. And these positive charges can couple well with the negative DNA or RNA, and they form this dendriplex. And people sometimes use them for gene delivery. So this is an illustration of the application of dendrimers. And here, let's do some math. So very straightforward. You have a line, right? You want to measure it out. So if your measuring stick is this big, you're measuring out one piece, okay? And if you cut your measuring stick into 2 pieces, you can measure out 2 pieces. You cut it into like 3 pieces, okay? The resolution is higher, you can cut the 3 parts, okay? So that's linear. And for a square, if you, how do I go back? Yeah, must be like this. Oh yeah. For a square, your measuring stick is cut by 2, you get 4. Okay. If you have a smaller measuring stick, you get 9. So you can see the formula here is the number of elements, number of squares you see, and this how many sticks. You know, the scale, kind of like the scale down factor. Okay. Now you have a 2, yeah. You have cut it by 2, your measuring stick, you get 8 pieces of the cube. And then 3, of course, you get 27. So dimensionality is defined as 1, 2, 3. Very simple. Does it make sense? It's a little confusing. This is scale down factor. It's how many pieces you cut your measuring stick. Okay? Yeah. The bigger the number, the smaller your scale. It's a reciprocal. Yeah. And so let's take a look at this one. This is interesting because you can see this is a line. You cut it into 3 parts, take out the central one, and then you seal it back up using this equilateral triangle. So here you have 4 segments, 1 into 4. and then so on. You can see on level 2, you can take this piece, cut it into 3 parts, take out the central one, and fix it back up like that, okay? So let's take a look at the formula. So when you reduce it to 1/3, you see the scale, right? To 1/3, and then you've got 4 pieces. When you reduce it by 1/9, right? And then you get 16 pieces. So you can calculate out the dimensionality. So the dimension here is a fraction. That's why it's called a fractal. It's self-similar. It goes on and on, infinite, right? Mathematically, you can do this. So let's take a look. Yeah, you can just keep amplifying, and it will never stop. Okay. So the length here, is infinite, but the area is finite. This has some good use. This is your neighbor. No longer part of UK, right? The British island, main island. You see how long is my coastline? That's the kind of like uncertain. It's a chaos, you know. It depends on how is your measuring stick. If it's very small, then you get a larger number, right? You get prouder of your country. Oh, very big number. Okay, so does it make sense? That's I want to instill a sense of uncertainty in our perception, okay, of the world. So here's another one. Here's another one. You have a triangle, okay? You cut out the central piece, okay? So therefore, when your measuring stick is this big, you can see one piece. When you reduce it by half, you will have 3 of them, okay? Can you see like the 3 piece and then 2? The dimensionality here, 1.5 something. So it's a fractal. It can go on and on like this. And there is a 3-dimensional one. Yeah, this is in a park. Yeah. So let's look at this one. This one, can you see the grid here? This is kind of like I don't know, fishbone. It superimposes onto the triangle. Yeah. So geometrically, this branching pattern is equivalent to the Sierpinski triangle. And I hope you can see this is not really like a tree, because a tree is very outgoing. It's growing towards the sun. It's all branching out. If your tree is like falling down like this, it's not really a healthy, a normal tree. Is that okay? So I just want to highlight that this pattern here has some difference from that pattern. And in reality, in technology, people use this type of a shape to design antennas or antenna. Okay. And this is a 3-dimensional one. This can optimize the receiving or sending of signals. These are important for engineer. But for us, we're chemists. So you can see that what we want to do is we want to focus on the difference between this shape and that shape. Okay. That shape is mimicked here. People know it's dendrimer, no problem. Dendri just means tree, right? Dendrimer is a tree-like molecule. And for us, we designed this molecule so that it can. I got too excited, a little bit touchy there. So what was I saying? So yeah, so this molecule is more equivalent to the branching patterns here. Can you see? Okay. So again, what we are trying to do is not to replicate math, because this is ideal. All the length here, they have a certain specific length. But what we are trying to do here is kind of get some impression, some inspiration from nature, fractal, and design a molecule. It may not be exactly the same length ratio, right? But we have chemistry, functional group. Yeah, we put on sulfur in the cyano groups. These can interact with metal species. So therefore, with this molecule, we want to interrogate it with metal species. What would you do? You are a fractal-like molecule, right? How would you behave if I ask you to, hey, form a framework or crystalline? Okay? Does it sound like fun? It's hard to get funding if you keep doing stuff like that. But So you can see you have silver ion here. It picks up 3. So you can see this molecule, you can treat it as like a tripod. And it forms a graphene-like structure. Okay, this is one layer. And these are your side chains. Yeah, can you see the side chains here are not participating, are not involved in that, right, in bonding. And there is a second layer they want to pack. They pack. It's easy, right? They're overlapping. So you can see that the main branches are forming this domain of a hexagonal wall, whereas the side chains, you can see that they are aggregating towards at the center. A lot of sulfur atoms. Out for silver. Okay, so they picked up a second set of silver atoms. So right off the bat, you can see the hierarchy here. You have the primary branch picking up the primary the silver, and the secondary branches picking up a second type of silver. You can see the clear divide. The molecule is very smart. Okay, you give me a hierarchy molecular structure, I give you a hierarchy, like a hierarchical network. These are the anions. They also follow the hexagonal pattern. Now I want to simplify it. Okay, I want to simplify this by using this purple grid to stand for the primary. And then I'm going to follow the secondary branches using the green. Okay, I'm going to get rid of everything. So this is from chemistry, from the molecule, right? The molecule gives us this answer. We interrogate it. Okay, that's what we get in terms of the mathematical pattern. Can you see we have a hierarchical structure in an infinite domain? Okay, these are like single crystals. They go on forever. This is called a hexagonal hierarchy. You know who first thought about this? It's somebody in Germany, here in southern Germany, called Kristaller. If you look it up on Wikipedia, you can see it's called the central place theory. Why in this part? At first, I didn't understand. This part is close to the Alps, but exactly very flat, a lot of area. So Kristaller then look at the cities. A big city usually is surrounded by 6 smaller cities. Yeah, and then it's also selected by so each one is also another surrounded by the villages. Or well, if you look at a hospital and then clinic, right, they follow this type of hexagonal distribution to maximize efficiency. Yeah. Okay. So this is in economic geography. So you want to open like a what do you call Starbucks with some other brand, you need to use this type of hierarchy. Okay. Yeah. In a flat area. And this is just a modern picture showing that in Midwest, that's where I was, Michigan, a very flat open field. You can see the big cluster and it's surrounded by smaller ones. Yeah. So our molecules is like human beings. The settlement is similar. And let's just have this one. And you can see there's another answer. The molecule give. Okay. You can see here the primary branch is. Let's look at the molecule. This is the molecule. This is the primary branch. And you see it picks up silver, but the silver is bonded to the secondary branch. This is the secondary branch, the yellow. Okay. So here the primary branch and the secondary branch, they are working together to form this node. And so that's pretty much what's going on. Previously, we have the clear divide of primary, secondary. It's a very hierarchical, right? Here, they are merging. They are merging together into this single sheet. But for general audience, you can see a hexagon, another hexagon, another big hexagon. Self similarity, okay? What's that? That's the Pinsky triangle. You look at it different, right? This is what people usually show you, a unit cell. And then people cut off that. If I cut off the 2 corners, I see the self-similarity pattern. And then here is the Sierpinski triangle. You see this molecule, this pattern here, okay? It's all connected. This is not a mistake. It's a Raphael, right? The painter, Italian painter. What do you see? You see, of course, the saint. Okay, so this is the religious. triangle, smaller triangle. So this pattern is very prevalent. It's everywhere. This is kind of the composition is a close reflection to our molecule and the crystal structure. So the overall structure is very daunting, very gigantic. The unit cell, you can see, this is our double layer, single layer, double layer, they alternate. The two layers, they are alternating each other, packed into a single crystal structure. It's solved by X-ray. You know, back then, the X-ray was already good. More math, more math. Math is difficult. So what are we seeing here? What we're seeing here is a simple formula, equation. So what we want to look at is the C number. We give it a C, and we start from x equals 0. And we use very simple, like Sn squared, okay? And we want to find this, let's look at different C, okay? C values and how it pans out, okay? How it pans out in terms of the number. So let's put in 1. C equals 1, okay? And then just do x, start always from 0, 0. And then you have x1 to 1, s2 2. Can you follow the number? Right? This is very straightforward. So this number goes on to be very big. It doesn't converge. It escapes, right? It explodes. So this one, C equals 1. Oh, it's here. You know, it's outside of this domain, okay? And then this is called the Mandelbrot set. What about -1? -1 is interesting because it's negative, right? It keeps pushing it back to like 1 and -1. So -1 is right here at the center here. So for all the ones that are converging, they are not exploding, right? We just put it inside. This the black area. All these numbers, they are converging. Okay, so let's look at a number of other 1.1. You see -1, periodic 1.38. So different numbers, their converging pattern or escaping pattern is different. Okay, you can see. Okay, so all these numbers, they are within this region, within this black region. This set. It's called the Mandelbrot set. Yeah, Mandelbrot. That's like almond bread, you know, in German. Yeah, very nice name. So the important thing is the edge. And you see the edge already looks very like complicated, complex. So what it says is on the edge, some numbers are converging. Right next to it, it's not converging. You change the number a little bit, that will change whether or not you converge or not. You see what I mean? So let's take a look. You see, this is mathematical, right? This little shape is repeating itself, yeah? So this goes on and on, it's infinite. This is the mathematical demonstration of self-similarity. Simple equation. You repeat it, right? All the numbers, they behave very sensitive. You change a little bit, it could become black or not black, okay? So this is another feature you see, right? You see the feature, the boundary, right? The edge. So in here, it's converged, right? Outside, it's not converging. Just this definition. You see, when you blow it up, it keeps repeating. It keeps repeating. Because nowadays, computers, it's easy, right? You can compute to 100 number, digit. You see, this is from Wikipedia. If you want, you can look it up. Very famous. Okay. In biology, the fractal is also an important concept. Okay, so it just keeps going and going. Just a simple equation. What does that say? That says that the boundary very complex. Well, I say that again, right? You change your number, you shift it a little bit. Well, the property is hard to predict, right? You could become converging one moment and you touch a little bit, it's not converging, it's exploding. So this is like the butterfly effect. What it says is that the flapping of the butterfly wings, right? They can set off a tornado, right? It's hard to predict a tornado. So this type of chaotic, yes, chaotic and unpredictable behavior is already seen. You kind of get a feel, right? The branching pattern makes it a little bit fuzzy to give a definitive answer. So you can see that the butterfly effect. The butterfly here is called the orange sulfur. It's a type. I don't know if you have orange sulfur in this part of Europe. And interestingly, I like the German language. Schmetterling, right? Is in German that was a butterfly. It starts with a S. Yeah, sulfur. And it sounds like chemistry, but it's biology. So don't put the demarcation too hard between us. Yeah, and philosophy even. You see, like this Taiki symbol also has the sulfur letter. Yeah, the S letter. It's kind of upside down. Okay, and sulfur turns out to be our favorite element. You see this molecule here? It has the sulfur groups fixed around the oxygen group. It's like the three branches, two sides. And then in chemistry, it turns out that sulfur is soft, polarizable. Oxygen is hard, has a higher charge density. So this kind of this is bifunctional molecule, you know, as hard and soft, kind of mimics the yin and yang binary characters. And with this rich functionality, they're complementary, yin and yang. Like in our society, usually I joke about it as a men and women, they create the world, right? So with this yin and yang thing, we can assemble this molecule into an extended framework. This is an infinite network, 2D, two-dimensional. Yeah. First off, we didn't say this 2D because it's a stacking. It's okay, 2D like, okay? And but if you like chemistry, this is zirconium. Zirconium picks up the oxygen, not to carboxylate it, without touching the sulfur. That's the chemistry behind it. Very simple. The zirconium thing was invented by first here in Germany and then in Norway. So we just use our chemical knowledge and we build a more sophisticated network. It's called the metal organic framework. Yeah. So this network, we can put it in a solar cell. This is the perovskite solar cell. And here is our network with the sulfur groups, right? This cell is protected, and then there is some lead in here, and our sulfur groups can capture the lead. That's some fundamental study trying to express it in a more applied form. Let's do this. And I want to reflect a little bit now, our cross-cutting approach in research, yeah? Because as an undergraduate in chemistry major, this is what you study. It's a molecules, right? You have the solution, titration is always in solution, and you study molecules, benzene, acetic acid. And these are discrete, isolated molecules. And then you, of course, this field of chemistry, organic chemistry also originated in Germany. Yeah, that's part of the reason I like studying German. Yeah, I can read all those original papers. Yeah, and it's already exploded. Now you can make peptides, you can make amino acid. What's it called? DNA, right? Sequencing. So the functions is enormous. Right? Organic chemistry. Look at this. This is Taxol. This is an anti-cancer drug. Total synthesis. Chemists, they can make it, right? Starting from the petroleum industries materials, right? So this field is very sophisticated. I don't have to convince you, okay? And then on the other side, what we have is something called the solid state chemistry. And this study looks on the solid state. Usually you need to grow crystals. Well, what do people look at is the regular packing array in the solid state. And they're constituent, right? Their components there are usually very simple. You know, they study like this is iron atoms. Just this is a layer, icosis packing. What's like the packing efficiency? This is what you learned in your structural chemistry course. Okay, so can you see the contrast of the two areas? One is isolated, the other is extended, right? Packing is important. How the individual components, how they overlap, the electrons get localized. You need to have a global, holistic view, right? They call it band structures, okay? And the other one, the one side very sophisticated. You indulge your love for making things. Okay. The other part is relatively simple, but it's technologically very important because it's this packing of iron. Right. If you have single iron atom, you don't talk about conductivity. You don't talk about conductivity of the bulk. Right. It's a result of the packing of numerous atoms. It's a collective behavior. So you see superconductivity. It's even more fancy, and porosity, you need to have an assembly to call for porosity. So these two fields usually are not connected, so what we have been trying to do because of some serendipity or the arrangement of fate, because I like organic chemistry, and I ended up in a group in Michigan in a solid state chemistry group. So it's kind of like an invisible hand guiding me. So I was fortunate to have my organic chemistry skill combined with the study of an extended structure in the solid state. So that's why it has been so much fun for me. Yeah. So building on our love of chemistry, we make more sophisticated molecules, assemble them in a solid state. And here you can see that we have a lot of sulfur groups clustered around because of this crystallization process. They are arranged around this cluster. And this high density of sulfur take up mercury. So you have your mercury, by the way, if you have mercury in your water, right, you just throw it out. You don't say, oh, I purify it. Okay, I recycle water. If it's mercury, it's dead, the water. Okay, because it's mercury. You're allowed to have 2 ppb, right? How can you like remove it by ppb, right? It's the baseline. So people don't recycle mercury water for drinking. Okay, so but in our system, you can see even if it's 300 times limit, and it becomes a 2 ppb. That's because of the unique arrangement of our sulfur. Okay, this is for demonstration. That's the curve there. And here we pair our molecules down. We don't want to go too complicated. We just use a single ring. And then we put on an alkene unit. This alkene unit can work with the sulfur. And this is the nuclear waste. In the nuclear waste, they have a lot of good stuff in there. Palladium, ruthenium, right? The thing is, how do you take it out? So you don't want the copper or iron. So with our molecule, because of the concerted effort from sulfur and alkene, the palladium is effectively taken out from the nuclear waste. And we can also build our molecules into a single crystal. And once you have palladium in there, it becomes red. It's the sensing. Palladium is important catalyst, by the way. So we have both the sensing and recycling agent developed from this simple molecule. Fractal, right? Branching motif. And in here, we even go further down for simplicity, using the sulfur atom and carboxylate. It's not as symmetrical as you see in a tree, right? That's why sometimes you need to make compromises. Our imperfect life, you don't want everything to work out perfectly for you. Okay, that's a little bit of fundamental stuff there. And so in this molecule, it turns out when it organizes into the solid state, you can see. This is for Daniel, by the way, because you're the chemistry professor. And then you can see that it's a layered structure. That in one layer, you have the sulfur concentrated in this layer, and they are electrolytically conducting, right? It's a sulfur metal interaction, very polarizable. This one layer. In the second layer here, you can see the sideway, right? You have ionic. It's only oxygen and the metal ion. So you have covalent and ionic components alternate. Okay, this is also the division. And this matches, by the way, the superconductors. In superconductors, usually have one covalent layer and ionic layer. They're closely coupled. Ours is also closely coupled. So that's what we are working on. We're trying to figure out if this is a really superconductor. Okay, that's some frontier that we are pushing at this point. Water wants a bubble. Water forms a soap bubble. And you see the soap bubbles, they come in different sizes. You have big and small. It's like a hierarchy. Yeah. Hierarchy is more important in China. The social structure. Oh, my hierarchy block. And then this is a more beautiful picture. You can see that the big ones, smaller ones, the bigger ones are smaller in number, of course, and the smaller ones are numerous. Okay. And here it's modeled by this mathematical model. They call it Apollonian gasket. Okay, so it's a mouthful. But you can see that it's also fractal. It kind of matches this tree pattern here. So soap bubble has a lot of scientific implications. And you can have also your soap film in this form. Yeah, this and this form here is very simple. You can see that this is like a saddle. You can sit on it. But if you sit on the other side, you do the same. So in math, it's called the same curvature on both sides. So this is a constant curvature or zero curvature throughout. A very comfortable saddle. Okay, and this is a minimize the surface area. When you have a lot of this piece, this simple saddle piece, you can assemble them. You can piece them together into a continuous form. It's called the continuous surface area. Okay, very beautiful. Do you agree? It's beautiful. It's nice. And so look at this. Can you see like we have a purple grid here, cubic, monkey bars, they call it in the States. And then you can fit this blue one right inside. This blue one is actually taking up the empty space. It's also a cube. So the monkey bar and the open space, they are the same structure. Voila, complementary. Talking about, yeah. So you can see. So since the blue and purple are complementary, you can have red or green. It's okay. You can put an interface between them. You can put this interface between the two cubic grids, and you get what you have in here. It's called the P surface. It's the mathematics is clear here. It's done. It's done. So in nature, usually we find three types of minimal surface areas, minimal surfaces. This one we just saw is a cube, 6 connected. This one is what? It's diamond. Diamond is 4. Okay, you have 2 diamond grid, and this is the surface in between. And here you have 3. It's called the gyroid surface. And this is a, remember this 3-dimensional. Okay, it goes on and on. In the cell membrane, you study chemistry. How does the cell accommodate an incoming entity? Right? Sometimes the membrane deforms, and they form some type of this bicontinuous minimal surface. So it's relevant because these mathematics are so fundamental. So you're going to see it no matter in chemistry or biology, or even in Munich. This is minimal surface. Can you see the? I don't know if they call it dot, right? The roof top there. Yeah. This is of course a very bigger scale, much bigger scale. And here for chemists, they want smaller. Yeah, they use a molecule. This molecule is called the surfactant. Surfactant in biology very common. The cell membrane, right? Bilayer, long tail, and then the head is hydrophilic. And when you have this one in water, the tail is repelled by water, so it forms this micelle. And the micelles, they can further condense. When you remove more water, they condense into this cylindrical form. It's called the hexagonal phase. Okay, so inside is the oily part, and then here are the silicon and the water. They're hydrophilic. And then you can just calcination is a fancy word for heating. to high temperature. Yeah. So, and then you get rid of your organic, and what you end up with is hollow tubes, right, packed all together. This is going on in the solid state. This is mesoporous. The pores are quite big for chemists, 3 nanometers, right? A molecule is maybe 1 nanometer, right? So these are bigger than a molecule. 3 nanometer. This is the artistic rendition here. So you can see the walls here are amorphous. It's disordered, whereas the pores are quite regular, and you can have 3 phases. Yeah? This is the bicontinuous phase. This is the more like the lipid bilayer. Okay, you can see different scale on different scale. The most interesting for us is we go to the atomic scale. We go to the atomic scale. You can see that this structure, this is called a zeolite. Zeolite is like a rock, yeah, rock, the stein. Okay, so it has the aluminum and oxygen silicon. It's in the beach, right? It's called the sodalite here. So can you see the atoms? They are mapped onto this P surface. Yeah. So in nature, you have the surface. It's everywhere. It's really hard to get away from it. But this one is hard to make. This is carbon. It's even more simple. You have the carbon-carbon bonds. They are less reversible because these are ionic. Under acid or base, they dissolve, they can reform, so you can recrystallize, like a protein crystal, right? You can recrystallize. But this one, how do you break the bond? Reversible. No, it's nonpolar. It's too strong. So this is called a 3D graphene analog. Okay, I know Christoph doesn't like the name 3D graphene. It's analog. Okay, I forgot the word. Yeah, yeah. All right. So this object is not made. Graphene, you know, I have 2D. It's in your pencil. So this one, it's not made. People are trying to make it. It's beautiful. It could be superconductor, for example, right? So I just want to share a little bit what we do in order to kind of achieve that structure. So we draw inspiration from this shape, the fractal shape. Can you see in the designing of a fractal shape here, we are actually concentrating a lot of carbon atoms. This is like a 3 bonds. This is a triple bond is like a carbon. It's an alkyne, right? This is pure carbon atoms. Yeah, we're like accidentally concentrating a lot of carbon atoms on the molecule. So whenever we pare it down a little bit, have the simpler form, we have more carbon atoms right at the center, okay? And we want to know if these concentrated carbon array can somehow transform into the 3D structure. So first you need order, right? If you just take your molecule, it's like a powder disorder, you heat it up and you get amorphous. There is no organization. There is no pre-positioning. So combining our knowledge of chemistry, organic chemistry, with a solid state chemistry, we have this extended array. Look at the structure. There's this crystal. It indicates order. So we ordered it in the solid state, and then we heat it up. We heat it up because this framework here is quite strong. You heat it up, but the carbon atoms aggregate. Okay. Eventually, with the even better chemistry, we need better catalysts. So maybe we can catalyze the transformation of these little pieces into a continuous ordered form of the structure. Okay, that was the ambition. This is my closing slide. You know, we have talked about freeze, right? This backfolded pattern, this fractal, and we design molecules to reflect the pattern. Of course, our molecules are simplified version of the complicated branchy, right? Stuff, the uncertainty, chaos, right? We are using our molecule to kind of, on a certain level, reflect this shape. And then we were talking about the butterfly, you know, butterfly thing is like flap the wing, it's tornado, right? It's a slide. Sometimes it's a lot of unpredictability. And this is our molecule, yeah. And also the soap. bubbles. They are also complicated. Okay? And still, we draw our inspiration and we set our target on this concrete molecular chemistry object. And then in our chemical expression, we have our molecules to reflect, right? To reflect the shape, but we instill the rich function of sulfur and oxygen to build useful networks. Okay, so I think the closing statement here is when we are looking at a complicated, apparently complicated nature, right? We want to understand it, but we feel our understanding is limited. There is always chaos. But in this process, what we want to achieve is within our ability, human beings, right, try to achieve some order out of this apparent appearance of chaos. Thank you for your attention.